Look up at the night sky. You see stars, maybe a planet or two, the faint glow of the Milky Way. But what if I told you that everything your eyes can perceive is just a fraction of the real story? Beyond the familiar tapestry of visible light, the universe holds a deeper, warmer secret, a hidden layer written in the language of heat. Imagine a gentle, all-pervading glow stretching across the entirety of space, invisible to our eyes but carrying within it the echoes of creation itself. This isn't science fiction. This is the cosmic infrared background, one of the most profound and mysterious discoveries in modern astronomy. This faint infrared light isn't just random noise, it's a cosmic fossil, a remnant from some of the earliest moments after the Big Bang. It holds clues to epochs so ancient that light itself was only just beginning to travel freely through the cosmos. Within this subtle glow lie answers to questions that have puzzled scientists for generations. How did the first galaxies form? What ignited the fires of the earliest stars? And could this background radiation even hint at the true nature of dark matter, the invisible scaffold holding our universe together? In this video, we're going to explore 25 of the most captivating mysteries hidden within the cosmic infrared background. From unseen primordial galaxies to the possibility of entire populations of stars that have never been directly observed, we'll unravel the secrets written in infrared light. This isn't just a story about telescopes and data. It's a journey to the edge of what we know and beyond. So come with me as we pull back the curtain on the heat glow of the cosmos and discover what the universe has been hiding in plain sight, just waiting for us to look a little closer. But to truly understand the first and perhaps greatest mystery, we have to ask a surprisingly simple question. Where is all this light actually coming from? We call it a background, which makes it sound like a smooth, uniform curtain of light, but that's where the mystery deepens. This glow isn't a single, simple thing, it's a cosmic chorus. A collective hum made up of the combined light from countless individual sources across the universe, all blending together into a single, faint signal by the time it reaches our telescopes. The primary singers in this choir are distant galaxies, but not the beautiful, spiral ones we often picture. These are galaxies shrouded in massive clouds of cosmic dust, where stars are being born at a ferocious rate. The dust absorbs the intense ultraviolet light from these newborn stars, heats up, and re-radiates that energy as the infrared glow we now detect as part of the background. Another major contributor is the intense radiation from active galactic nuclei, supermassive black holes at the hearts of galaxies, consuming matter and blazing with incredible energy, also often hidden behind thick veils of dust. So the cosmic infrared background is essentially the combined heat signature of all the hidden, violent, and dramatic star-forming events that have ever occurred throughout cosmic history, all piled on top of one another. The challenge for astronomers is the ultimate exercise in cosmic forensics. They are presented with this single, faint smear of light and must find a way to disentangle it, to figure out how much comes from which epoch, and to identify the specific types of objects responsible. This is incredibly difficult because we have our own local pollution to contend with. Our solar system is filled with tiny dust particles, remnants from comet trails and asteroid collisions. Sunlight scatters off this dust, creating a phenomenon called zodiacal light, which also shines brightly in the infrared. This local glare is a powerful foreground that astronomers must meticulously subtract from their data, like trying to hear a whisper at a rock concert. Peering through this local haze to isolate the faint, ancient cosmic signal is the first and most fundamental step in unlocking the secrets held within this primordial heat. And that brings us to our second great mystery, a hunt for the ghosts of creation. We're searching for the very first stars to ever ignite in the cosmos, a generation of stars so ancient and pure that we've never directly seen one. Astronomers call them population 3 stars. To understand why they're so special, we have to rewind the clock nearly to the very beginning. After the Big Bang, the universe was a dark, swirling soup of just two elements, hydrogen and helium. There was no carbon, no oxygen, no iron, none of the heavier elements that are essential for building planets or even stars like our own sun. So when the first stars finally coalesced from these pristine clouds of gas, they were fundamentally different from anything that exists today. Without heavier elements to help them fragment and cool, these stars grew to absolutely monstrous sizes. We're talking behemoths that could be hundreds of times more massive than our sun. And with enormous mass comes ferocious power. These first stars would have lived fast and died young, burning at searing temperatures and shining with a blistering, ultraviolet intensity that made them visible across the young cosmos. Their lives were short, ending in spectacular supernova explosions that, for the very first time, seeded the universe with those heavier elements, the cosmic ingredients for everything that would follow, including us. But here's the catch: we've never found one, not a single definitive population 3-star. They all burned out and died billions of years ago. So how do we search for something that vanished so long ago? We look for their echo. The theory is that the collective ultraviolet light from that first generation of stars didn't just disappear. As the universe expanded, that energetic light was stretched or redshifted on its epic journey across space and time. By the time it reaches us over 13 billion years later, that once fierce ultraviolet glow has been transformed into a faint whisper of infrared light. And that whisper should, in theory, be woven into the very fabric of the cosmic infrared background. The problem is isolating it. It's not a single, distinct note in the cosmic chorus. It's more like trying to pick out the sound of one specific violin from a recording of a massive symphony played at the very edge of hearing. Astronomers look for subtle patterns, tiny irregularities in the background glow called anisotropies, where the infrared signal is ever so slightly brighter or fainter in certain patches of sky. Within those minute fluctuations could lie the statistical signature of those first stellar giants. Finding that fingerprint would be like discovering the first chapter of the universe's history book, giving us a direct glimpse into the era when the first lights switched on and began to transform a dark, empty cosmos into the brilliant universe we see today. It remains one of the most sought-after prizes in all of astronomy. Now we come to a pivotal crossroads in cosmic history, a dramatic transformation known as the epoch of reionization. For hundreds of millions of years after the Big Bang, the universe was a very different place. It wasn't filled with glittering stars and galaxies as far as the eye can see. It was a vast, opaque fog. The space between galaxies was filled with a thick soup of neutral hydrogen gas that effectively trapped light, making the entire cosmos a kind of dim, featureless prison. But then something happened. Something caused this fog to lift, burning away the neutral hydrogen and turning it into a transparent, ionized plasma, the clear universe we observe today. The question is, what provided the incredible amount of energy needed to accomplish this? What were the cosmic engines powerful enough to illuminate the entire universe? This is one of the most significant open questions in cosmology, and the cosmic infrared background holds a crucial piece of the answer. Scientists are locked in a heated debate over the primary driver of this great cosmic clearing. Was it a colossal number of small, faint sources or a smaller number of incredibly powerful ones? On one side of the argument, we have the proponents of dwarf galaxies. The idea here is that the universe was absolutely teeming with countless small, early galaxies, each one actively forming its first generations of stars. While individually faint, their collective output of ultraviolet radiation could have been immense. Think of it like a massive city viewed from a great distance at night. You might not be able to pick out any single small house light, but the combined glow from millions of them creates an unmistakable haze that lights up the entire sky. This scenario suggests that the work of reionization was a communal effort, a slow and steady process driven by the sheer number of these small stellar factories. On the other side of the debate are the champions of quasars. These are not gentle giants, they are the most violently energetic objects in the universe. A quasar is a supermassive black hole at the center of a galaxy that is actively devouring colossal amounts of matter. As this material spirals inward, it heats up to incredible temperatures and blazes with a light so intense it can outshine its entire host galaxy. A single quasar can produce a devastatingly powerful beam of ultraviolet radiation, a cosmic blowtorch capable of ionizing vast volumes of space all on its own. In this scenario, reionization might have been a more dramatic and uneven process, with these brilliant beacons punching huge, transparent bubbles in the neutral fog around them before eventually merging. So how do we settle this argument? We can't just go back in time to watch it happen. This is where the cosmic infrared background becomes our most valuable time capsule. It effectively acts as a ledger, recording the total energy output from all sources during this critical period. The key is that the energy required to ionize all the hydrogen in the universe, the so-called energy budget for reionization, is a known quantity. The combined infrared light we measure in the CIB represents the waste heat from all the ultraviolet light that was produced by these early sources. A significant portion of that UV light didn't escape to do the work of ionization. It was instead absorbed by cosmic dust within those same galaxies, which then re-radiated it as the infrared glow we see today. By carefully measuring the total amount of energy locked within the cosmic infrared background, astronomers can work backwards. They can calculate the minimum number of ultraviolet photons that must have been produced to both account for this infrared waste heat and still have enough left over to fully ionize the universe. This places a critical constraint on the population of early objects. If the total energy in the CIB is very high, it implies an absolutely staggering number of faint dwarf galaxies were needed to produce it. If the energy is lower, it leaves more room for fewer but far more powerful quasars to have done the heavy lifting. Current measurements are increasingly pointing towards a universe where the countless faint galaxies are the dominant contributors, suggesting that the dawn of light was a story of collective effort rather than a few brilliant dictators. The infrared background is the hard evidence that lets us weigh these competing theories, providing a fundamental check on our models of how the universe first turned on the lights. This leads us directly to our fourth great mystery, which is perhaps the most profound of all. The cosmic infrared background is essentially the universe's ultimate history book, a complete record of star formation across all of time. Every star that has ever burst into existence has left its mark on this background glow. Here's how it works. When a star is born, it doesn't just shine with visible light, it unleashes a torrent of intense ultraviolet radiation. But in the dusty nurseries where most stars form, that brilliant UV light rarely escapes directly. Instead, it's almost immediately absorbed by the thick clouds of cosmic dust surrounding it. This dust heats up much like asphalt gets hot under the summer sun and then re-radiates that captured energy, but at much longer infrared wavelengths. So, the violent, brilliant act of a star's birth is ultimately translated into a warm, infrared whisper. The CIB is the sum total of all those whispers, a fossil record of every star-forming event that has ever occurred, all the way back to the very first ones. This gives us a tool of incredible power. If we can accurately measure the total energy in the cosmic infrared background, we are effectively measuring the total number of stars ever formed. It's like taking a cosmic census that counts every single citizen, not just the ones who are easy to see. This is where the mystery truly deepens, because when astronomers compare this infrared census to the history of star formation they've pieced together by directly observing galaxies, the numbers don't add up. For a long time, our view of the universe's history was built by painstakingly pointing our most powerful telescopes at tiny patches of sky, counting and measuring the light from individual galaxies we could see, and then extrapolating outwards. This method suggested a relatively gentle and steady rise in the rate of star formation, peaking around 8 to 10 billion years ago and then gradually declining to the quieter pace we see today. But the CIB tells a completely different and far more dramatic story. It reveals that there is a vast amount of star formation that these direct surveys have simply missed. An enormous portion of the universe's stellar population is effectively hiding in plain sight. Some of these galaxies are so shrouded in dust that their visible and ultraviolet light is completely blocked, making them invisible to traditional surveys. Others are incredibly faint, either because they are extremely far away or because they are small, dwarf galaxies whose collective light was too dim for our telescopes to detect individually. The infrared background doesn't miss them. It captures their combined heat signature, revealing that the early universe was a far more violent and prolific stellar factory than we ever imagined. The peak of cosmic star formation might have been earlier, faster, and more intense than our direct observations suggested. This missing star formation is a monumental piece of the puzzle, forcing us to rewrite the timeline of how galaxies assembled and evolved. It suggests epochs of incredible frenzy, where entire galaxies were turning their gas into stars at a ferocious, unsustainable pace, their brilliant births hidden behind impenetrable cosmic curtains of dust. The CIB is the key that unlocks this hidden history, revealing a universe that was far more active, dynamic, and extreme in its youth than we could have ever discovered by simply looking at the light we can see. But if the cosmic infrared background is the universe's history book, then these tiny fluctuations, these anisotropies, are the individual sentences written within it. We've established that this infrared glow is the collective heat from countless hidden sources, but if it were perfectly smooth and uniform, it would tell us very little. Its true power lies in its imperfections, in the subtle, clumpy patterns of slightly brighter and slightly dimmer patches that appear when we map it with extreme precision. These are not random noise or errors in our instruments. They are a deliberate signature, a cosmic fingerprint left by the way matter is organized across the largest scales imaginable. Think of it like looking down at a city from a high-flying airplane at night. From that great height, you can't make out individual cars or even specific houses. Instead, you see the glow of the city itself, and within that glow, you can clearly see brighter clusters and darker patches. Those bright clusters trace the outlines of neighborhoods, downtown districts, and major highways, the underlying structure of the city. The anisotropies in the cosmic infrared background do exactly the same thing, but for the entire universe. They trace the cosmic web, the vast, invisible skeleton of dark matter upon which all visible structures are built. This happens because galaxies, especially in the early universe, are not scattered randomly through space like sprinkles on a cupcake. Gravity pulls them together. They form clusters, those clusters form long filaments, and those filaments connect at dense nodes, creating a gigantic web-like structure with enormous voids in between. The galaxies that contribute most to the infrared background, those dusty, star-forming galaxies, are also strongly clustered within this web. So, the patches of the sky where this web is most dense will have a higher concentration of these infrared galaxies, and thus will appear slightly brighter in the CIB map. The voids where there are far fewer galaxies will appear correspondingly darker. By meticulously measuring the size and distribution of these bright and dark patches, astronomers can perform a kind of statistical archaeology. They can decode the clustering properties of galaxies that are far too faint to ever see individually. It allows us to ask profound questions. How tightly were these early galaxies grouped together? How does that clustering change depending on how far away they are, which also means how far back in time we are looking? The answers tell us not just about the galaxies themselves, but about the fundamental laws of the universe. The way structures clump together over time is exquisitely sensitive to the nature of dark matter and dark energy. Different models of dark matter, for example, predict different clustering patterns. Some theories suggest dark matter particles are cold, moving slowly and clumping easily to form the web we see. Others propose warm, dark matter, which would suppress the formation of very small-scale structures, leading to a subtly different pattern in the anisotropies. By comparing the statistical map gleaned from the CIB fluctuations to the predictions of these different models, we can effectively rule some ideas out and lend support to others. This makes the study of these infrared anisotropies one of our most powerful tools for probing the most mysterious components of our cosmos. We are using the faint, accumulated light of hidden stars to illuminate the invisible scaffolding of dark matter that has dictated the evolution of everything we can see. It's a remarkable chain of inference, from a subtle variation in a heat glow to the distribution of unseen galaxies, all the way to the core properties of the universe's most dominant yet elusive substance. Yet for all its power, the map of the cosmic infrared background is not without its own puzzling features, and some of the most intriguing come from unexpected discrepancies right here in our own cosmic neighborhood. This brings us to our next pair of mysteries, which revolve around strange excess light that our instruments have detected. The first comes from a sounding rocket experiment named CIBER, the Cosmic Infrared Background Experiment. Unlike a space telescope that stays in orbit for years, a sounding rocket makes a short, 15-minute flight into space before falling back to Earth. But in that brief window, CIBER was designed to do one thing with extreme precision: measure the absolute brightness and the pattern of fluctuations in the near-infrared background at wavelengths that are incredibly difficult to observe from within our atmosphere. What it found was startling. The experiment detected large-scale fluctuations in the infrared glow that were far brighter than anyone had predicted. This wasn't just a little extra light. It was a significant excess that couldn't be explained by the combined light of all the known galaxies we've catalogued. It was as if we had meticulously counted every single house light in our metaphorical city at night, only to discover that the overall glow of the city was still somehow brighter than the sum of those parts. This CIBER excess points to a completely unknown source of infrared light pervading the cosmos. One compelling and somewhat haunting explanation is that we are seeing the collective glow of stars that have been violently ripped from their homes. Throughout cosmic history, as galaxies collide and merge in a violent gravitational dance, countless stars can be torn from their host galaxies and thrown out into the lonely, dark voids of intergalactic space. These orphan stars, sometimes called intrahalo stars, would drift forever in the emptiness between galaxies, shining faintly. Individually, they are far too dim and spread out for any telescope to ever see. But their combined, diffuse light could add up, creating a subtle, all-pervading glow that blankets the entire universe. This background of lost suns could be the source of the extra infrared fluctuations that CIBER detected, a ghostly testament to the violent interactions that have shaped galaxies across time. Other, more exotic explanations have also been proposed, including light from the decay of certain types of hypothetical dark matter particles. The key point is that the CIBER result, along with similar findings from the Japanese IRTS satellite, tells us that there is a component of the infrared background we do not yet understand, a source of light that is fundamentally diffuse and not tied to any specific galaxy we can point a telescope at. This observational puzzle is deeply connected to a second mystery, one that lies at the heart of how we search for the most distant galaxies. For decades, the gold standard technique for finding galaxies from the early universe has been the Lyman break dropout method. It's a brilliantly clever trick. We know that neutral hydrogen gas in the universe absorbs light at a very specific wavelength in the ultraviolet, known as the Lyman limit. As light from a distant galaxy travels across the expanding universe, its light is stretched or redshifted. For a galaxy with a high enough redshift, this key absorption feature is stretched all the way from the ultraviolet into the visible or even infrared part of the spectrum. This means that in certain filters on our telescopes, the galaxy will suddenly seem to drop out or disappear because its light has been absorbed by this universal hydrogen fog. By comparing images taken through different filters, astronomers can efficiently pinpoint these dropout galaxies and estimate their distance. However, this powerful technique has a critical and potentially huge blind spot. It only works for galaxies that are actually emitting plenty of that ultraviolet light to begin with. It perfectly finds young galaxies filled with hot, blue, massive stars shining brightly in the UV. But what if a galaxy in the early universe was already filled with dust? Perhaps it was forming stars at a tremendous rate, but all of that brilliant ultraviolet light was being immediately absorbed by its own thick dust clouds and re-radiated as infrared light. To a telescope using the Lyman break technique, this dusty galaxy would be completely invisible. It wouldn't have the strong ultraviolet signal to drop out, it would just be absent from the search. This means our entire census of the early universe, built primarily on the Lyman break method, could be systematically missing an entire population of galaxies, not because they are too faint, but because their light is being emitted in a different language that our traditional surveys are not designed to read. This missing population of dusty, early galaxies is a prime candidate to explain not only the CIBER excess, but also the significant portion of the total cosmic infrared background that remains unaccounted for by known galaxies. We are likely blind to some of the universe's most intense stellar nurseries, hidden in plain sight because they conducted their brilliant cosmic business behind a veil of their own making. This brings us to two of the most fundamental and intertwined mysteries of the early cosmos, questions not about light itself, but about the very nature of matter. What is the source of the heat, and what is the nature of the material that gets hot? First, we must consider a radical possibility that a significant portion of the infrared background isn't from stars or galaxies at all, but from the death throes of the universe's most hypothetical and ancient objects, primordial black holes. The black holes we know and study today are stellar mass black holes, formed from the collapse of massive stars, and supermassive black holes that sit at the centers of galaxies. Primordial black holes are something else entirely, theorized to have been created not from dying stars, but from the extreme densities and pressures in the first fleeting moments after the Big Bang. These would be true relics of creation. They could span a vast range of sizes, from smaller than an atom to many times the mass of our Sun. Here's where the connection to the infrared background gets fascinating. According to Stephen Hawking's revolutionary work, black holes aren't completely black. They slowly evaporate over astronomical timescales by emitting a faint glow of particles, now known as Hawking radiation. For a massive black hole, this process is incredibly slow, and its radiation is incredibly cold and undetectable. But for a very small black hole, the story is completely different. The smaller a black hole is, the faster it evaporates, and the hotter and brighter its Hawking radiation becomes. A primordial black hole with a mass of around 1 billion metric tons, roughly the mass of a large mountain, would have a lifetime that lasts about the current age of the universe. And right now, at this very moment, any such black holes reaching the end of their lives would be evaporating in a spectacular flash of high-energy radiation, including gamma rays. But if we look back to the early universe, the scene would be different. A whole population of slightly larger primordial black holes would have been evaporating at that earlier time, and as they did, they would have released their energy as a pervasive thermal heat. This heat would have been redshifted by the expansion of the universe, and by the time it reaches us, it could manifest as a contribution to the faint, uniform glow of the cosmic infrared background. The idea is that we might be detecting the collective cosmic sigh of countless tiny black holes blinking out of existence, their final energy forever imprinted on the infrared sky. While there is no conclusive evidence for this yet, it remains a captivating and profound possibility that the CIB could be the funeral pyre of the universe's first black holes. This speculation about the source of the heat is immediately followed by an equally puzzling question about the material that produces the heat we know is there, the cosmic dust itself. We've talked about how dust is essential. It's the material that absorbs starlight and re-radiates it as the infrared glow. But this presents a monumental chicken and egg problem for the early universe. Dust doesn't just appear, it has to be manufactured. The heavy elements like carbon, silicon, and oxygen that form the core of dust grains are forged only in the nuclear furnaces of stars and then scattered into space when those stars die, primarily in supernova explosions or in the powerful winds from aging giant stars known as asymptotic giant branch or GB stars. This process takes time. A massive star lives for only a few million years before going supernova, which is brief on cosmic scales, but a GB star is a sun-like star that must live out its entire multi-billion-year life cycle before it can produce and expel dust. And herein lies the enigma. We see clear evidence from the cosmic infrared background and from observations of the earliest galaxies that the universe was already extremely dusty when it was less than 1 billion years old. This is astonishingly fast. It means that the first stars had to form, live, die, and seed their surroundings with heavy elements, and then a second generation of stars had to form from that enriched material and also die, all within the first few 100 million years of cosmic history. For GB stars, the timeline is even more strained, as they typically require billions of years to evolve. This forces a dramatic reevaluation of how quickly the cosmic cycle of life and death could begin. It suggests that the first supernova must have been incredibly efficient dust factories, perhaps the most prolific in history, creating immense quantities of solid material in their explosive aftermath. Alternatively, it might point to other, more exotic and rapid dust production mechanisms, such as the dense winds erupting from quasars. The presence of so much dust so early is a direct physical clue that the first chapters of the universe were not a slow, stately progression, but a frenzied and explosive period of creation and destruction, setting the stage for everything that was to come. The cosmic infrared background, therefore, is not just a record of light. It is a record of the frantic effort to build the very ingredients of planets and life from the ashes of the first stars. The challenge of identifying the true sources of the cosmic infrared background leads us directly into two of the thorniest observational debates in modern astrophysics. The first is a fundamental dispute over the universe's primary power plants, a controversy centered on active galactic nuclei, or AN. We know the CIB is the total thermal waste from all the ultraviolet light ever produced, but the critical question is, what fraction of that light came from the furious nuclear fusion inside stars, and what fraction came from the terrifying gravitational fury of matter screaming into supermassive black holes? This isn't just an academic accounting exercise. The answer dictates our entire understanding of how cosmic structures evolved and how energy was distributed to shape the universe. On one side of this debate, you have the argument for star formation as the dominant driver. This view paints a picture of the early universe as a place of incredible, widespread stellar birth, where countless galaxies were furiously converting gas into stars, their collective output drowning out everything else. The opposing view grants a much larger, more pivotal role to AGN. In this scenario, the brilliant, piercing light from these accreting black holes wasn't just a sideshow, it was a primary actor. The energy pouring out of a single quasar can outshine an entire galaxy, and that energy doesn't just light up the cosmos, it regulates it. This intense radiation can heat vast reservoirs of galactic gas, preventing it from cooling and collapsing to form new stars, effectively shutting down star formation in its vicinity. This process, called quasar feedback, is thought to be a critical mechanism that governs the growth of galaxies. If AGN contributed a substantial portion of the energy in the CIB, it means they were not rare monsters but common and integral features of the early universe, their influence woven into the very fabric of cosmic evolution. Untangling this is incredibly difficult because the two sources are often found together and can look remarkably similar in the infrared. A galaxy that is both forming stars at a ferocious rate and hosting an active black hole will produce a tremendous amount of dust-heated infrared light. From a great distance, separating the contribution of the star-forming regions from that of the central AGN is like trying to distinguish the sound of a roaring waterfall from the sound of a powerful jet engine when you're standing miles away. They both just blend into a loud roar. Astronomers use sophisticated statistical methods to try and tease them apart, looking for subtle differences in the brightness and color of the infrared emission. The current consensus is leaning towards star formation being the dominant contributor to the overall background, but the precise percentage attributed to AGN remains one of the largest uncertainties in our models. Getting this number right is essential. It's the difference between a universe shaped primarily by the birth of stars and one sculpted equally by the destructive power of black holes. But even as we argue over the nature of distant power sources, we face an even more immediate and deceptive challenge much closer to home, the veil of galactic cirrus. Our own Milky Way galaxy is filled with immense, wispy clouds of cold dust and gas. When these clouds are warmed slightly by the light from our galaxy's stars, they themselves emit a faint infrared glow. From our vantage point inside the Milky Way, this emission isn't just in the background, it's all around us in the foreground. And unfortunately, this faint, warm cirrus can look almost identical to the faint, uniform signal of the true extragalactic cosmic infrared background. It's the ultimate case of cosmic contamination. Imagine you're trying to listen to a very faint, distant radio station, but someone in your own house is constantly humming the same tune at almost the exact same volume. Your brain would struggle to separate the two sounds. That's precisely the problem astronomers face. This cirrus confusion forces scientists to become masters of cosmic forensics. They must create exquisitely detailed maps of this local dust emission across the entire sky, using data from telescopes like Planck and IRS, and then meticulously subtract it from their observations to reveal the genuine extragalactic signal hiding beneath. The problem is, this subtraction is never perfect. If they over-subtract, they risk removing real parts of the CIB, making it appear fainter than it truly is. If they under-subtract, they leave behind this local contamination, which could masquerade as a mysterious, smooth excess in the background or alter the measured patterns of the anisotropies. This delicate, painstaking process is a major source of systematic error and debate in the field. Some of the large-scale fluctuations detected by experiments like CIBER could in fact be partly due to our incomplete understanding of the structure and emission of this local Milky Way cirrus. Before we can be certain of what the distant universe is telling us, we must first fully understand the whispered secrets of our own galactic home. To truly grasp the full story the cosmic infrared background is telling us, we need to follow the journey of the universe's raw material, the normal matter or baryons that make up everything we can see and touch. This is the great cosmic baryon cycle, and the CIB acts as a vital tracer for one of its most pivotal phases. The cycle begins with vast, pristine clouds of hydrogen and helium gas left over from the Big Bang. Over eons, gravity pulls these clouds together, causing them to collapse and fragment, eventually igniting into brilliant new stars. These stars then flood their surroundings with intense ultraviolet radiation. But in the dusty environments where stars are born, that radiant energy doesn't simply escape into space. It's captured by the dense clouds of dust grains, microscopic particles of carbon and silicate that surround these stellar nurseries. The dust absorbs the high-energy light, heats up, and then re-emits it at the longer, warmer wavelengths of infrared light. This process is the crucial link that allows the CIB to serve as a direct record of star formation. The infrared glow we detect is essentially the thermal echo of that initial gravitational collapse, the waste heat from the universe's monumental effort to turn diffuse gas into shining stars. By measuring this background, we are effectively auditing the universe's energy budget, tracking how much baryonic matter has completed this transformative journey from cool gas to luminous star to warm dust. This cycle, however, doesn't end there. The fate of that dust is just as important. The intense radiation pressure from newborn stars, combined with the shock waves from supernova explosions, can push this dust-enriched material back out into the circumgalactic medium, the vast, sparse reservoir of gas that surrounds a galaxy. From there, some of this material might eventually fall back into the galaxy, fueling new generations of stars in a process of cosmic recycling. Alternatively, it can be lost entirely, ejected into the even emptier intergalactic void. The CIB helps us understand the efficiency of this entire process. The amount of infrared light produced tells us not only how many stars formed, but also how much dust was present to absorb their light, giving us clues about the density and distribution of baryons throughout cosmic history. It reveals epochs where the baryon cycle was running at a fever pitch, with galaxies consuming gas and producing stars and dust at an astonishing, unsustainable rate. But this grand cycle of material doesn't stay neatly contained within the dazzling disks of galaxies we see in telescope images. A significant portion of it is flung into the darkness, leading to our next profound mystery, the glow of intrahalo light. Galaxies are not isolated islands. Each one is embedded within an enormous, diffuse sphere of dark matter called a halo. These halos are the true gravitational anchors of galaxies, and they are not empty. They are filled with a sparse population of stars and clouds of dust that have been gravitationally ripped from their host galaxies during violent interactions and mergers. When two galaxies collide, a common occurrence in the crowded early universe, their stars rarely crash into one another. Instead, the immense tidal forces pull and stretch them, flinging countless stars out into the surrounding dark matter halo. These stars are now orphans, forever bound to the halo's gravity but divorced from the bright lights of their galactic home. This creates a phenomenon known as intrahalo light, a faint, diffuse glow emanating from these lonely stars and the dust that travels with them. Individually, each of these stars is far too dim to be seen across cosmic distances, but their collective output, spread across the immense volume of a dark matter halo, can add up to a significant, pervasive infrared signal. Because this light is not concentrated in a small, bright point like a galaxy, but is instead smeared out across a huge area, it is incredibly difficult for our telescopes to detect directly. We can't take a picture of it in the traditional sense. However, this is precisely where the large-scale fluctuations in the cosmic infrared background become our most valuable tool. This diffuse intrahalo glow would contribute a specific kind of signal to the CIB's pattern of anisotropies, a signature of clumpiness on scales that match the size of these vast dark matter halos. When experiments like CIBR detected an excess of large-scale fluctuations, one of the leading explanations was that they were finally seeing the accumulated infrared light from this missing population of halo stars throughout the cosmos. This would mean that a substantial fraction of all the stars ever formed might actually live out their lives in this bleak intergalactic exile, their combined faint warmth adding a subtle, ghostly veil to the infrared background. The CIB, therefore, is more than a record of star formation within galaxies. It is a testament to the violent chaos of galactic evolution and the countless stars lost to the darkness between them. But to move beyond these local challenges and truly decode the ancient message of the cosmic infrared background, we must turn to one of the most powerful techniques in the modern cosmologist's toolkit: cross-correlation. On its own, a map of the CIB is like a single, mysterious voice in a crowded room. It's full of information, but it's difficult to isolate and understand. The real magic happens when we listen to that voice in harmony with another, completely different cosmic signal. By cross-correlating the infrared background with other, independent traces of mass and structure in the universe, we can break through the confusion and pinpoint exactly when and where this ancient light originated. One of the most profound partnerships is between the CIB and the cosmic microwave background, or CMB. While the CMB is the remnant heat from the Big Bang itself, and the CIB is the accumulated starlight of billions of years, they are connected through a remarkable physical process called the Sunyaev-Zeldovich effect. This occurs when the CMB's photons travel through the universe and interact with the incredibly hot electrons that are present in massive galaxy clusters. These high-energy electrons give the CMB photons a slight boost in energy, leaving a distinct, cold imprint on the CMB map that precisely traces the location of those massive clusters. Now we know that the same massive structures, the clusters and the filaments of the cosmic web that create this SZ effect are also the environments that host the dusty, star-forming galaxies responsible for the CIB. So, when astronomers cross-correlate a map of the CIB with a map of the SZ effect from the CMB, they are effectively asking a powerful question: does the pattern of infrared light align with the pattern of the most massive structures in the universe? The answer is a resounding yes. The two maps show a significant correlation. This tells us two crucial things. First, it confirms that the sources of the CIB are indeed strongly clustered within the universe's large-scale structure, just as we suspected. Second, and more importantly, because the SZ effect is more sensitive to structures at specific distance ranges, this cross-correlation allows scientists to weigh the contribution of different cosmic epochs. They can determine how much of the infrared background comes from relatively near-by sources versus how much is from incredibly distant, ancient galaxies, effectively slicing the CIB in time and breaking the degeneracy that makes a single map so difficult to interpret. Another powerful cross-correlation is done with the distribution of visible galaxies from large-scale surveys. By comparing the clumpiness of the infrared background to the clumpiness of galaxies we can directly see, astronomers can perform a kind of statistical census of the hidden population. If the CIB fluctuations are much more strongly clustered than the visible galaxies in a certain patch of sky, it implies the presence of a whole host of faint, dusty galaxies that are too dim to see individually but whose collective signal is captured in the infrared. This technique doesn't just tell us these galaxies exist, it can even provide estimates of their brightness and how numerous they must be to account for the extra signal. It's like hearing the roar of a massive crowd outside a stadium, and by comparing it to the number of people you can see through the gates, accurately estimating just how many thousands of unseen fans are actually out there. This brings us to one of the most fascinating and unexpected connections in all of astronomy: the intimate relationship between the universe's faintest glow and its most violent explosions. For this, we turn our attention to the realm of very high-energy gamma rays, particles of light with energies trillions of times greater than what our eyes can see. These gamma rays are produced by the most extreme engines in the cosmos, particularly blazars, a special type of galaxy whose supermassive black hole is firing a jet of radiation and particles directly toward Earth. As these powerful gamma rays race across the universe toward our telescopes, they don't always complete their journey unscathed. They can collide with the lower energy photons that make up the cosmic infrared background. When a high-energy gamma-ray photon smashes into a low-energy infrared photon, it's an encounter governed by Einstein's famous equation. The collision is so violent that it converts the energy of both particles into new matter, creating an electron and a positron. This process, called pair production, effectively means the gamma-ray is absorbed. It vanishes from the beam. This interaction has a dramatic and observable consequence. The farther away a blazar is, the more of the infrared background its gamma rays have to travel through, and the more likely they are to be absorbed before they reach us. Therefore, the spectrum of a distant blazar, the graph of its brightness across different gamma ray energies, doesn't just tell us about the blazar itself. It carries a distinct imprint, a sort of faint shadow, of the entire sea of infrared photons it had to pass through. By carefully measuring how the light from blazars at different distances is attenuated, astronomers can work backwards to measure the density and the spectrum of the CIB itself. It's an incredible indirect measurement. We are using the most energetic particles in the universe as a probe to study the softest, most ancient heat glow. This technique has provided some of our most robust constraints on the total intensity of the infrared background, independently confirming the measurements from direct observations and helping to rule out potential sources of local contamination. The fact that the gamma rays from the most distant blazars are significantly absorbed tells us that the universe was already filled with a substantial amount of infrared light when those gamma rays began their journey billions of years ago. This is a powerful, independent validation that the CIB is indeed a cosmological signal, a fundamental property of the universe that has shaped the journey of light across the deepest reaches of space and time. But even as we use these brilliant techniques to map the grand structure of the infrared background, we face two deeply fundamental and intertwined problems that strike at the very heart of observational cosmology. The first is a puzzle of cosmic color known as the spectral energy distribution. Think of the light from any object as a unique rainbow or a fingerprint that tells you about its temperature, composition, and distance. The cosmic infrared background has its own spectrum, a specific curve that describes how bright it is at each different infrared wavelength. Constructing this definitive overall spectrum is our single best tool for figuring out what the sources of the background actually are, because different types of objects produce different spectral signatures. The heat from swirling disks of dust around young stars creates a very different infrared rainbow than the blazing torus of dust around a supermassive black hole. If we could just get a perfect, clean measurement of the CIB's spectrum, we could essentially take it apart, identifying the precise mix of galaxies, stars, and perhaps even more exotic objects that combine to create it. The challenge, however, is that we don't have one single perfect measurement. Instead, we have a collection of conflicting clues from a fleet of the world's most powerful infrared observatories, each with its own strengths and quirks. The Spitzer Space Telescope provided exquisitely sensitive data at certain mid-infrared wavelengths. The Japanese AKRI satellite covered a broader wavelength range with different calibration. The European Space Agency's Herschel Observatory gave us an unparalleled view of the far infrared, where the coldest dust radiates. Individually, each mission's data is a masterpiece of engineering. But when scientists try to combine them all to paint one unified picture of the CIB's spectrum, the pieces don't always fit together neatly. Small differences in how each instrument was calibrated or how each team modeled and subtracted other sources of light lead to discrepancies. It's like having three world-class musicians trying to play the same symphony, but one's violin is tuned just a hair sharp and another's cello is slightly flat. The result isn't a clear melody, but a dissonance that makes it incredibly difficult to decode the true cosmic score. This spectral puzzle means that key questions remain open. Exactly how much of the background is from warm versus cold dust? Does the spectrum show features that could only be explained by entirely new populations of objects? Until we can reconcile these datasets, the full story hidden within the CIB's light remains tantalizingly out of focus. This brings us to the second, and perhaps most daunting, challenge of all, the overwhelming glare from our own cosmic backyard. To see the faint, ancient light of the CIB, we must first peer through what is arguably the greatest contaminant in all of astronomy: zodiacal light. If you've ever been in a very dark location just before dawn or after dusk, you might have seen a faint, ethereal pyramid of light reaching up from the horizon. This glow isn't from the Milky Way or any distant star. It is sunlight reflecting off countless tiny dust particles that fill the inner solar system. This vast lens-shaped cloud of interplanetary dust, remnants from asteroids and comets, orbits the Sun along with the planets, and while it appears faint to our eyes, in the infrared it is devastatingly bright. This is because the dust isn't just reflecting sunlight, it is also being warmed by the Sun and re-radiating that heat. To an infrared telescope in space, the zodiacal light is not a subtle phenomenon. It is an intense, all-pervading foreground glow that can be 10 to 100 times brighter than the faint cosmic infrared background we are desperately trying to measure. Dealing with this local pollution is the ultimate exercise in precision and patience. Astronomers cannot simply ignore it or point their telescopes away from it. It is everywhere. Instead, they must become masters of modeling this complex cloud. They map its intricate structure by carefully measuring how its brightness changes as the Earth moves through the cloud and as the telescope's viewpoint changes throughout the year. They use every scrap of data available to understand the density, composition, and temperature distribution of this solar system dust. Then, with painstaking care, they create a digital model of its emission across the entire sky and subtract it from their observations. The success of every measurement of the CIB hinges entirely on the accuracy of this subtraction. If the model is even slightly off, if it underestimates the zodiacal light by just 1%, that error will be left behind in the data, masquerading as a smooth, extragalactic signal. Conversely, if the model over-subtracts, it can erase real features of the genuine CIB. This delicate operation is the reason why measurements of the absolute brightness of the infrared background are so fiercely debated. Some of the most intriguing anomalies and excesses reported over the years, including those from the CIBER rocket experiment, could potentially be explained not by distant galaxies or orphan stars, but by subtle, unaccounted-for structures within our own solar system's dust cloud. Before we can be certain we are hearing the faint whisper of the first galaxies, we must be absolutely certain we have silenced the roar from our own solar neighborhood. For decades, the primary challenge of the cosmic infrared background has been its unresolved nature, that maddening blend of countless faint sources into a single, smooth glow. Our best telescopes simply weren't powerful enough to see the individual trees within this ancient forest. But now we have entered a new era of cosmic observation, one that is finally turning this blur into a sharp, focused picture. The James Webb Space Telescope was in many ways designed for this exact purpose. With its colossal, gold-coated mirror and its suite of exquisitely sensitive infrared instruments, Webb is doing what was once thought impossible. It is resolving a significant fraction of the cosmic infrared background into its individual constituent galaxies. We are no longer just studying the glow, we are meeting the sources face to face. Webb's deep field images are not just beautiful, they are revolutionary data sets. In patches of sky that once appeared dark or only sparsely populated to the Hubble Space Telescope, Webb is revealing a universe teeming with faint red smudges. Each one is a distant galaxy, its light stretched into the infrared by the expansion of the universe. Crucially, a large number of these newly discovered galaxies are incredibly dusty, exactly the type of objects that were predicted to be the main contributors to the CIB, but were too faint and too red for previous telescopes to detect. By counting these galaxies and measuring their individual infrared brightness, Astronomers are now conducting a direct census. They are adding up the light from all these newly resolved sources to see how much of the mysterious background glow they can finally account for. Early results are stunningly successful, with Webb resolving a much larger percentage of the background than any observatory before it. This is the moment of validation for decades of theoretical work. We are finally identifying the specific galaxies responsible for building the cosmic infrared background, confirming that a vast population of hidden, dusty stellar nurseries was indeed the missing piece of the puzzle all along. Yet, even as Webb solves one major mystery, its incredible sensitivity opens the door to another, even more exotic possibility. As we peer deeper and subtract the light from all the galaxies we can now see, a question remains: does a perfectly smooth, residual glow persist? Is there a component of the infrared background that is truly diffuse, not tied to any galaxy, no matter how faint? This is where we venture into the realm of speculative but profoundly thrilling physics, the dark matter annihilation hypothesis. We know that dark matter makes up about 85% of all the matter in the universe, yet we have no idea what it actually is. One of the leading candidates is a theoretical particle known as a WIMP, a weakly interacting massive particle. According to some models, these WIMP could be their own antimatter counterparts. This means that when two dark matter particles collide, they could annihilate each other in a flash of energy, converting their mass directly into other particles, including gamma rays and, importantly, lower energy infrared photons. In the early universe, the density of dark matter was immense, and these annihilations would have been far more frequent than they are today. This process could have produced a vast number of photons that would have been redshifted by the expansion of the universe, potentially contributing a faint, uniform component to the cosmic infrared background. The key signature would be in the pattern of the fluctuations. The glow from annihilating dark matter would not be clumpy like the light from galaxies clustered in the cosmic web. Instead, it would be exquisitely smooth, with a very specific pattern of anisotropies that reflects the distribution of dark matter on the largest scales. Some cosmologists have pointed to certain large-scale fluctuations in the CIB that seem slightly too smooth to be explained by galaxies alone, suggesting this could be the faint, indirect signal of dark matter revealing itself at last. It is a long shot, and the evidence is far from conclusive, but the mere possibility is electrifying. The James Webb Space Telescope and other future observatories will scour the residual, unresolved background for any hint of this perfectly smooth signal. Finding it would be a discovery of Nobel Prize-winning magnitude, providing our first ever glimpse into the nature of the universe's most dominant yet mysterious substance, not through a laboratory experiment on Earth, but by reading its ancient infrared signature written across the entire sky. This search for the dawn of light leads us to two intertwined mysteries that force us to rewrite the very first chapters of our cosmic story. The first is the hunt for a specific, ghostly imprint within the infrared background itself, a signature of the cosmic dawn, that pivotal moment when the very first stars and black holes switched on and ended the universe's dark ages. We're not just looking for their light, we're searching for a specific pattern within that light that could only have been created by those primordial objects. One of the most promising avenues is the study of polarization. Light can be polarized, meaning its waves vibrate in a preferred direction. The theory suggests that the ultraviolet light from the very first stars could have been polarized as it escaped its dusty nursery or as it scattered off the electrons in the early universe. That polarization signature, imprinted over 13 billion years ago, would have been preserved as that light was stretched into the infrared, potentially leaving a faint, ordered pattern within the otherwise chaotic glow of the CIB. Finding this would be like discovering the fossilized brushstrokes on a painting from the dawn of time, giving us not just a picture of the first light, but a clue to the physical conditions present at its birth. Another potential signature lies in the spectrum, the first stars being made of pure hydrogen and helium would have had a specific and unique thermal signature. Their dust, too, if it existed that early, would have had a different composition, potentially creating a subtle bump or dip in the overall infrared spectrum at very specific wavelengths that our telescopes could, in theory, detect. Isolating this signal is like trying to hear a single, pure note played on a flute that was lost in the roar of a massive orchestra that started playing immediately afterward. It requires instruments of unimaginable sensitivity, but the potential payoff is the ultimate prize, a direct physical measurement of the universe's first sunrise. What makes this search so critical is that it connects directly to the second part of our mystery, the obscured evolution of galaxies. The cosmic infrared background is our single greatest piece of evidence that a huge amount of cosmic construction was hidden behind closed doors. For decades, our view of galaxy evolution was based on what we could see in optical and ultraviolet light, which led to a relatively clean picture. Galaxies slowly grew over time by merging and acquiring gas. But the CIB screamed that this picture was incomplete. It revealed that there was an enormous amount of energy, the thermal waste heat from furious activity, that was completely missing from our optical senses. This forces us to confront a radical idea. A significant and perhaps dominant phase of galaxy growth and black hole building was heavily shrouded in dust. We now believe there were epochs, particularly in the early universe, when entire galaxies were enshrouded in thick, choking clouds of dust. Inside these cosmic cocoons, stars were being born at a ferocious, almost apocalyptic rate, and supermassive black holes were gorging on matter, growing to immense sizes. But from the outside, if you are looking with a telescope like Hubble that sees visible light, these galaxies would be utterly invisible. All the brilliant ultraviolet light from their stellar nurseries and the blazing radiation from their black holes was being immediately absorbed by the dust and re-radiated as infrared light. The CIB is the collective glow of all these hidden factories. It is the direct evidence that the universe went through a kind of hidden growth spurt, a period of intense, obscured activity that has only been revealed by its infrared heat signature. This means some of the most massive galaxies and black holes in the universe today might have gained most of their mass during this veiled era, their most dramatic growth hidden from view until now. The cosmic infrared background is the thermal echo of that secret history, proving that the most important chapters of galactic evolution were not written in the light we can see, but in the heat we have only just begun to feel. But our cosmic motion isn't just a singular curiosity. It provides a powerful, independent test of one of cosmology's most foundational principles, the cosmological principle. This principle states that on the largest scales, the universe is homogeneous and isotropic. It should look the same in every direction. The CMB is the strongest evidence we have for this, as it is incredibly smooth and uniform. The dipole we see in the CMB is accepted to be entirely due to our local motion. The underlying background itself is isotropic. The cosmic infrared background gives us a completely separate way to check this. Because the CIB is made up of light from galaxies spread across cosmic history, its dipole should also be caused solely by our motion. If we measure the CMB dipole and it matches the direction and magnitude of the CMB dipole, it's a resounding confirmation that the universe is in fact isotropic. However, if there were a significant discrepancy, if the CMB dipole were stronger or pointed in a slightly different direction, it could signal something revolutionary. It might suggest that the universe is not perfectly isotropic on the largest scales, or that there is a subtle, underlying anisotropy woven into the distribution of galaxies themselves. Precise measurements are incredibly difficult, buried under the glare of local foregrounds, but early results generally support the standard picture, using the infrared sky to reinforce our understanding of a uniform cosmos. This exploration of the universe's grandest structure leads us to a much smaller, yet equally perplexing puzzle, the missing satellite problem. Our leading model of the universe, the lambda-cold dark matter model, is spectacularly successful at explaining the large-scale cosmos. But when supercomputer simulations run this model to see how galaxies form, they produce a startling prediction. The dark matter halo of a galaxy like our Milky Way should be swarming with thousands of smaller satellite dark matter halos. These should be massive enough to host their own small, faint dwarf galaxies. Yet, when we look around our local galactic neighborhood, we only find a few dozen such satellites. Where are the rest? Are the simulations wrong about the nature of dark matter? Or are the satellites actually there, but we just can't see them? This is where the diffuse nature of the cosmic infrared background offers a fascinating potential solution. What if those missing satellites aren't actually missing at all? What if they are simply too faint, too devoid of the bright stars that make galaxies easy to spot, to be detected by our current optical surveys? These could be ultra-faint dwarfs, galaxies so dominated by their dark matter content that they have only managed to form a scant population of stars. Individually, each one would be incredibly dim, a ghost of a galaxy, but collectively across the entire universe their numbers would be staggering. The combined infrared light from all these countless faint stellar populations, the warm glow of their limited star formation, could contribute a significant diffuse component to the CIB. In this elegant scenario, two profound mysteries could be solved simultaneously. The missing satellite problem is resolved because the satellites aren't missing. They're just too dark for us to see individually with current technology. And a portion of the cosmic infrared background, particularly its large-scale fluctuations, is explained as the cumulative heat signature of this vast, hidden population of dark matter-rich dwarf galaxies. We are thus using the universe's faint heat glow to illuminate the invisible scaffolding of dark matter itself, providing indirect evidence for the legions of tiny halos that our theories demand but our telescopes have yet to directly resolve. As we near the end of our journey, we arrive at two final, deeply interconnected mysteries that speak not just to the origins of the cosmic infrared background, but to its ultimate meaning and the profound journey its light has taken. The first of these asks us to consider the possibility of a cosmic self-regulation mechanism, an imprint of the universe's own feedback on its creative process. We've discussed how the first stars and galaxies flooded the cosmos with ultraviolet radiation, carving out transparent bubbles during the epoch of reionization. But this incredible release of energy didn't just clear the fog, it had a lasting, suppressive effect. This radiation didn't only ionize hydrogen, it heated the vast reservoirs of gas throughout and between galaxies to incredibly high temperatures. Hot gas is energetic and resistant to collapse. For new stars to form, giant clouds of gas need to cool down and condense under their own gravity. By heating the gas, the intense radiation from the first generations of stars effectively slammed the brakes on later star formation, particularly in the smallest, most vulnerable dwarf galaxies. This process, known as radiative feedback, fundamentally shaped the subsequent evolution of the universe, determining which galaxies continued to grow and which were stunted, their potential for future stars extinguished. This grand act of cosmic regulation didn't happen silently. Theory suggests it should have left a specific statistical fingerprint on the distribution of infrared light. The process would have preferentially suppressed star formation in certain environments, particularly in lower density regions and smaller dark matter halos. This means the pattern of the CIB's fluctuations, the specific way its brightness varies across the sky, should carry a subtle signature of this ancient feedback. On the largest scales, the pattern should reflect the underlying cosmic web of dark matter, but on somewhat smaller scales, there might be a detectable deficit of power, a slight smoothing of the fluctuations, indicating where the formation of faint, small galaxies was throttled back billions of years ago. Finding this specific dip in the power spectrum of the anisotropes would be like discovering the fossilized tide marks of the universe's first great energy wave, a direct record of how the brilliant dawn of starlight itself ultimately limited the universe's future potential for creation. It would show us that the cosmos carries within its infrared glow not just a record of what was built, but also a memory of what was prevented from being built, a testament to its own self-regulating nature. This brings us to our final mystery, one that is less about astrophysics and more about our own place in the cosmos. We must pause to consider the ultimate fate of these individual photons that make up the cosmic infrared background. Each one is a messenger on an almost unimaginable journey. Its story began over 10 billion years ago, in the heart of a violent stellar nursery or the fiery disk around a supermassive black hole in a galaxy so distant its visible light has long since faded from view. A torrent of ultraviolet light was absorbed by a tiny grain of dust, causing it to vibrate with heat. In that moment, a new infrared photon was born. It was then emitted, beginning a voyage across an expanding universe that would last for eons. For billions of years, this particle of light traveled through an almost perfect void, a lonely emissary from an era when the universe was in its tumultuous youth. It survived near misses with distant galaxies, its path gently bent by the gravity of unseen dark matter halos. It persevered through the entire history of our planet, from its formation to the rise of life, all while streaming silently through the void. And then, finally, its journey ended. It streaked into our solar system, passed by the planets, and encountered a remarkable technological marvel, the polished, cold mirror of a space telescope built by a species on a small, watery world. It was focused onto an exquisitely sensitive detector engineered to capture its faint energy. In that instant, a connection was made across billions of light years and billions of years. The photon's journey, which began during the universe's childhood, ended by providing a crucial piece of data in humanity's quest to understand its origins. The cosmic infrared background is more than a scientific curiosity. It is the universe's own history, written in the language of heat and delivered to our doorstep by light that has been traveling for most of cosmic time. By learning to read this history, we are not just solving astronomical puzzles. We are engaging in a profound act of cosmic archaeology, piecing together the story of our own genesis from the faint, warm echoes of creation that still wash over us, connecting us directly to the deepest past. And so our journey through these 25 mysteries brings us full circle, back to a simple yet staggering realization. The cosmic infrared background is so much more than a faint smear of leftover heat on a telescope sensor. It is a dynamic, information-rich data stream, a continuous broadcast from the entire history of the cosmos, and we have only just begun to learn how to tune it in. It encodes the epic story of how nothing became something, how a smooth, hot soup of particles evolved into the magnificent, web-like structure of galaxies, stars, and planets we see today. Every fluctuation, every wavelength, every subtle anisotropy is a chapter in that story, speaking of the first stars to ever ignite, the violent feedback of supermassive black holes, the countless stars lost to intergalactic space, and the possibility of dark matter itself making its presence known through a faint, universal glow. Unlocking these secrets has demanded nothing less than a revolution in our approach to astronomy. It requires the sheer, awe-inspiring light-gathering power of telescopes like the James Webb Space Telescope to finally resolve this ancient glow into its individual galactic sources. It calls for the brilliant application of sophisticated statistical methods to tease apart the subtle patterns hidden within the noise, and the creation of bold, visionary theoretical ideas to explain what we find. This is not a solitary pursuit. It is a symphony of engineering, physics, and human curiosity, all working in concert to translate the universe's thermal whisper into a narrative we can understand. Each puzzle we solve about this infrared enigma brings us closer to answering the most fundamental questions we can ask. Where did we come from? How did the universe around us come to be? And what is the true nature of the vast, invisible cosmos that governs it all? The most exciting part is that this story is still being written. New data streams in every day from observatories around the world and in space, each new observation challenging our assumptions and offering fresh clues. The mysteries of the cosmic infrared background are not static puzzles to be solved and filed away. They are living, evolving questions that will undoubtedly reshape our understanding of the universe in the years to come. So I encourage you to stay curious, follow the new discoveries, the new images from Webb, the new theories that emerge from these incredible datasets. Because the faint heat glow of the cosmos still has countless secrets left to share, and the next great revelation could be just over the horizon. But the story of the cosmic infrared background is far from over. In many ways, we are just getting started. The next decade promises a revolution in our ability to read this ancient thermal text, thanks to a new generation of space observatories designed with this very purpose in mind. Leading this charge is NASA's SPHEREx mission, scheduled to launch in the next few years. Unlike telescopes that stare deeply at a single patch of sky, SPHEREx is a surveyor, an unparalleled cartographer of the entire infrared heavens. Its mission is to map the sky in over 96 distinct color bands, from the optical to the infrared, creating the most detailed spectral map of the universe ever attempted. This is a game changer. For the first time, we won't just see the brightness of the infrared background, we will know its precise color at every single point. This spectral fingerprint will allow us to do something previously impossible: cleanly separate the light from different cosmic eras. We'll be able to isolate the contribution from nearby galaxies, peel it away, and see the pristine infrared glow from the most ancient sources with a clarity we've never had before. SPHEREx will effectively create a three-dimensional map of the universe's thermal history, allowing us to trace the evolution of the infrared background through time itself, and finally pinpoint exactly when the universe was at its dustiest and most active. Following closely behind is the Nancy Grace Roman Space Telescope, a powerhouse with a field of view 100 times larger than the Hubble Space Telescopes. Roman's wide-eyed gaze is perfectly suited for tackling the problem of large-scale fluctuations. It will conduct massive, deep surveys of the infrared sky, not just in a few tiny deep fields, but across enormous swaths of the cosmos. This will allow astronomers to measure the pattern of anisotropies in the CIB with stunning statistical precision, mapping the clustering of those hidden, dusty galaxies across the vast cosmic web. With Roman's data, we can move beyond simply detecting these fluctuations to truly understanding what they mean. By comparing the clustering strength at different infrared wavelengths, which correspond to different distances, we can track how the hidden galaxy population evolved and how their relationship to the dark matter scaffolding changed over billions of years. Roman will help us definitively determine the role of intrahalo light, weigh the contribution of dwarf galaxies versus quasars, and provide the sharpest test yet for the dark matter annihilation hypothesis by searching for that telltale smooth signal across the entire sky. Together, these observatories will achieve what was once a distant dream. They will resolve the vast majority of the cosmic infrared background into its individual sources. The faint, blurry glow that has puzzled us for decades will sharpen into a pointillist masterpiece of countless distinct galaxies. We will have a nearly complete census of the universe's stellar output, finally accounting for that missing star formation and writing the definitive history of how galaxies built their stars. But perhaps the most exciting prospect is not the answers they will provide, but the new questions they will inevitably raise. Every time we have built a telescope with a new level of sensitivity, we have uncovered phenomena we never predicted, entirely new classes of objects that force us to rethink our models. There is no reason to believe this time will be any different. As SPHEREx and Roman peel back the final layers of the infrared sky, they will almost certainly reveal anomalies and features that we cannot currently explain. They might detect a spectral signature that points to an exotic form of dust from the very first stars, or a clustering pattern that suggests a previously unknown connection between dark matter and galaxy formation. The ultimate legacy of these missions will be to ensure that the study of the cosmic infrared background remains at the very forefront of cosmological discovery, continuously challenging our perception of the universe and reminding us that for every mystery we solve, a deeper, more profound one is waiting just beyond the light we can currently see.